Solar sails are a form of spacecraft propulsion using the radiation pressure from stars to push large ultra-thin mirrors to high speeds. Light sails could also be driven by energy beams to extend their range of operations, which is strictly beam sailing rather than solar sailing. Solar sailcraft offer the possibility of low-cost operations combined with long operating lifetimes. Since they have few moving parts and use no propellant, they can potentially be used numerous times for delivery of payloads. Solar sails use a phenomenon that has a proven, measured effect on spacecraft. Solar pressure affects all spacecraft whether in interplanetary space or in orbit around a planet or small body. A typical spacecraft going to Mars, for example, will be displaced by thousands of kilometers by solar pressure, so the effects must be accounted for in trajectory planning, which has been done since the time of the earliest interplanetary spacecraft of the 1960s. Solar pressure also affects the attitude of a craft, a factor that must be included in spacecraft design. The total force exerted on an 800 by 800 meter solar sail, for example, is about 5 newtons at Earth's distance from the Sun, making it a low-thrust propulsion system, similar to spacecraft propelled by electric engines. History of concept. Johannes Kepler observed that comet tails point away from the Sun and suggested that the Sun caused the effect. In a letter to Galileo in 1610, he wrote, "Provide ships or sails adapted to the heavenly breezes, and there will be some who will brave even that void." He might have had the comet tail phenomenon in mind when he wrote those words, although his publications on comet tails came several years later. James Clerk Maxwell, in 1861–64, published his theory of electromagnetic fields and radiation, which shows that light has momentum and thus can exert pressure on objects. Maxwell's equations provide the theoretical foundation for sailing with light pressure. So by 1864, the physics community and beyond knew sunlight carried momentum that would exert a pressure on objects. Jules Verne, in From the Earth to the Moon, published in 1865, wrote, "There will someday appear velocities far greater than these, of the planets and the projectile, of which light or electricity will probably be the mechanical agent. We shall one day travel to the Moon, the planets, and the stars." This is possibly the first published recognition that light could move ships through space. Pyotr Lebedev was first to successfully demonstrate light pressure, which he did in 1899 with a torsional balance. Ernest Nichols and Gordon Holt conducted a similar independent experiment in 1901 using a Nichols radiometer. Albert Einstein provided a different formalism by his recognizing the equivalence of mass and energy. He simply wrote P equals E, C as the relationship between the momentum, the energy, and the speed of light. Svante Arrhenius predicted in 1908 the possibility of solar radiation pressure distributing life spores across interstellar distances, providing one means to explain the concept of panspermia. He apparently was the first scientist to state that light could move objects between stars. Friedrich Zander published a technical paper in 1925 that included technical analysis of solar sailing. Zander wrote of using tremendous mirrors of very thin sheets, and using the pressure of sunlight to attain cosmic velocities. Konstantin Tsiolkovsky first proposed using the pressure of sunlight to propel spacecraft through space and suggested using tremendous mirrors of very thin sheets to utilize the pressure of sunlight to attain cosmic velocities. J.B.S. Haldane speculated in 1927 about the invention of tubular spaceships that would take humanity to space and how wings of metallic foil of a square kilometer or more in area are spread out to catch the sun's radiation pressure. J.D. Bernal wrote in 1929, a form of space sailing might be developed which used the repulsive effect of the sun's rays instead of wind. A space vessel spreading its large, metallic wings, acres in extent, to the full, might be blown to the limit of Neptune's orbit. Then, to increase its speed, it would tack, close, hold down the gravitational field, spreading full sail again as it rushed past the Sun. The first formal technology and design effort for a solar sail began in 1976 at Jet Propulsion Laboratory for a proposed mission to rendezvous with Halley's Comet. Physical principles. Solar radiation pressure. Solar radiation exerts a pressure on the sail due to reflection and a small fraction that is absorbed. The momentum of a photon or an entire flux is given Einstein's relation, P equals E, C, where P is the momentum, E is the energy, and C is the speed of light. Solar radiation pressure can be related to the irradiance value of 1361 W per square meter at 1 astronomical unit, as revised in 2011. Perfect absorbance. F equals 4.54 micronewtons per square meter in the direction of the incident beam. Perfect reflectance. F equals 9.08 micronewtons per square meter in the direction normal to surface. An ideal sail is flat and has 100% specular reflection. An actual sail will have an overall efficiency of about 90%, about 8.17 micronewtons per square meter, due to curvature, wrinkles, absorbance, re-radiation from front and back, non-specular effects, and other factors. The force on a sail and the actual acceleration of the craft vary by the inverse square of distance from the Sun, and by the square of the cosine of the angle between the sail force vector and the radial from the Sun. So F equals F0 cos 2 theta, R2, where R is distance from the Sun in O. An actual square sail can be modeled as F equals F0, R2. Note that the force in acceleration approach zero generally around theta equals 60 degrees rather than 90 degrees as one might expect with an ideal sail. If some of the energy is absorbed, the absorbed energy will heat the sail, which re-radiates that energy from the front and rear surfaces, depending on the emissivity. Solar wind. The flux of charged particles blown out from the Sun exerts a nominal dynamic pressure of about 3 to 4 nanopascals, 3 orders of magnitude less than solar radiation pressure on a reflective sail. Sail parameters. Sail loading is an important parameter, which is the total mass divided by the sail area, expressed in gram per square meter. It is represented by the Greek letter sigma. A sailcraft has a characteristic acceleration, at which it would experience at 1 astronomical unit when facing the Sun. Using the value from above of 9.08 micronewtons per square meter of radiation pressure at 1 astronomical unit, AC is related to areal density by AC equals 9.08 sigma millimeter per square second. Assuming 90% efficiency, AC equals 8.17 sigma millimeter per square second. The lightness number, lambda, is the dimensionless ratio of maximum vehicle acceleration divided by the Sun's local gravity. Using the values at 1 astronomical unit, lambda equals AC 5.93. The lightness number is also independent of distance from the Sun because both gravity and light pressure fall off as the inverse square of the distance from the Sun. Therefore, this number defines the types of orbit maneuvers that are possible for a given vessel. The table presents some example values. Payloads are not included. The first two are from the detailed design effort at JPL in the 1970s. The third, the lattice sailor, might represent about the best possible performance level. The dimensions for square and lattice sails are edges. The dimension for Heliagira is blade tip to blade tip. Attitude control. An active attitude control system is essential for a sailcraft to achieve and maintain a desired orientation. The required sail orientation changes slowly in interplanetary space, but much more rapidly in a planetary orbit. The axe must be capable of meeting these orientation requirements. Attitude control is achieved by a relative shift between the craft's center of pressure and its center of mass. This can be achieved with control vanes, movement of individual sails, movement of a control mass, or altering reflectivity. Holding a constant attitude requires that the axe maintain a net torque of 0 on the craft. The total force and torque on a sail, or set of sails, is not constant along a trajectory. The force changes with solar distance and sail angle, which changes the billow in the sail and deflects some elements of the supporting structure, resulting in changes in the sail force and torque. Sail temperature also changes with solar distance and sail angle, which changes sail dimensions. The radiant heat from the sail changes the temperature of the supporting structure. Both factors affect total force and torque. To hold the desired attitude, the axe must compensate for all of these changes. Constraints in Earth orbit. Solar pressure and drag pressure are typically equal at an altitude of about 800 kilometers, which means that a sailcraft would have to operate above that altitude. Sailcraft must operate in orbits where their turn rates are compatible with the orbits, which is generally a concern only for spinning disk configurations. Sail operating temperatures are a function of solar distance, sail angle, reflectivity, and front and back emissivities. A sail can be used only where its temperature is kept within its material limits. Generally, a sail can be used rather close to the Sun, around 0.25 astronomical units, or even closer if carefully designed for those conditions. Applications. Potential applications for sailcraft range throughout the solar system, from near the Sun to the comet clouds beyond Neptune. The craft can make outbound voyages to deliver loads, or to take up station keeping at the destination. They can be used to haul cargo and possibly also used for human travel. Inner planets. For trips within the inner solar system, they can deliver loads and then return to Earth for subsequent voyages, operating as an interplanetary shuttle. For Mars in particular, the craft could provide economical means of routinely supplying operations on the planet. According to Jerome Wright, the cost of launching the necessary conventional propellants from Earth are enormous for manned missions. Use of sailing ships could potentially save more than $10 billion in mission costs. Solar sailcraft can approach the Sun to deliver observation payloads or to take up station-keeping orbits. They can operate at 0.25 astronomical units or closer. They can reach high orbital inclinations, including polar. Solar sails can travel to and from all of the inner planets. Trips to Mercury and Venus are for rendezvous and orbit entry for the payload. Trips to Mars could be either for rendezvous or swing by with release of the payload for aerodynamic braking. Outer planets. Minimum transfer times to the outer planets benefit from using an indirect transfer. However, this method results in high arrival speeds. Slower transfers have low arrival speeds. The minimum transfer time to Jupiter for a of 1 mm per square second with no departure velocity relative to Earth is 2 years when using an indirect transfer. The arrival speed is close to 17 km per second. For Saturn, the minimum trip time is 3.3 years, with an arrival speed of nearly 19 km per second. Oort cloud. Sun's inner gravity focus. The Sun's inner gravity focus is a point, at about 550 astronomical units in the inner Oort cloud, at which light from distant objects is focused by gravity as it passes the Sun. This is thus an ideal distance from which to observe the region of deep space on the other side of the Sun. A small team had initially proposed a beryllium-inflated sail that would go down to 0.05 astronomical units from the Sun in order to get an acceleration peaking at 36.4 meters per square second, reaching a speed of 0.00264 c in less than a day. Such proximity to the Sun could prove to be impractical in the near term due to the structural degradation of beryllium at high temperatures, diffusion of hydrogen at high temperatures, as well as an electrostatic gradient generated by the ionization of beryllium due to the solar wind, posing a burst risk. Thus a revised perihelion of 0.1 astronomical units was proposed to reduce the aforementioned temperature and solar flux exposure. Such a sail would take 2.5 years to reach the heliopause, 6.5 years to get to the Sun's inner gravitational focus, with arrival at the inner Oort cloud in no more than 30 years. Such a mission could perform useful astrophysical observations en route, explore gravitational focusing techniques, and image Oort cloud objects while exploring particles and fields in that region that are of galactic rather than solar origin. Satellites. Robert L. Forward pointed out that a solar sail could be used to modify the orbit of a satellite around the Earth. In the limit, a sail could be used to hover a satellite above one pole of the Earth. Spacecraft fitted with solar sails could also be placed in close orbits about the Sun that are stationary with respect to either the Sun or the Earth, a type of satellite named by Forward is at height. This is possible because the propulsion provided by the sail offsets the gravitational potential of the Sun. Such an orbit could be useful for studying the properties of the Sun over long durations. Likewise, a solar sail-equipped spacecraft could also remain on station nearly above the polar terminator of a planet, such as the Earth, by tilting the sail at the appropriate angle needed to just counteract the planet's gravity. In his book The Case for Mars, Robert Zubrin points out that the reflected sunlight from a large statite placed near the polar terminator of the planet Mars could be focused on one of the Martian polar ice caps to significantly warm the planet's atmosphere. Such a statite could be made from asteroid material. Trajectory corrections. The messenger probe orbiting Mercury used light pressure on its solar panels to perform fine trajectory corrections on the way to Mercury. By changing the angle of the solar panels relative to the Sun, the amount of solar radiation pressure was varied to adjust the spacecraft trajectory more delicately than possible with thrusters. Minor errors are greatly amplified by gravity assist maneuvers, so using radiation pressure to make very small corrections saved large amounts of propellant. Interstellar flight. In the 1970s, Robert Forward proposed two beam-powered propulsion schemes using either lasers or masers to push giant sails to a significant fraction of the speed of light. In Rocheworld, Forward described a light sail propelled by super lasers. As the starship neared its destination, the outer portion of the sail would detach. The outer sail would then refocus and reflect the lasers back onto a smaller, inner sail. This would provide braking thrust to stop the ship in the destination star system. Both methods pose monumental engineering challenges. The lasers would have to operate for years continuously at gigawatt strength. Forward's solution to this requires enormous solar panel arrays to be built at or near the planet Mercury. A planet-sized mirror or Fresnel lens would be needed, several dozen astronomical units from the Sun to keep the lasers focused on the sail. The giant braking sail would have to act as a precision mirror to focus the braking beam onto the inner deceleration sail. A potentially easier approach would be to use a maser to drive a solar sail, composed of a mesh of wires with the same spacing as the wavelength of the microwaves. Since the manipulation of microwave radiation is somewhat easier than the manipulation of visible light, the hypothetical star-wisp interstellar probe design would use microwaves, rather than visible light, to push it. Masers spread out more rapidly than optical lasers owing to their longer wavelength, and so would not have as long an effective range. Masers could also be used to power a painted solar sail, a conventional sail coated with a layer of chemicals designed to evaporate when struck by microwave radiation. The momentum generated by this evaporation could significantly increase the thrust generated by solar sails, as a form of lightweight ablative laser propulsion. To further focus the energy on a distant solar sail, Forward proposed a lens designed as a large zone plate. This would be placed at a location between the laser or maser and the spacecraft. Another more physically realistic approach would be to use the light from the Sun to accelerate The ship would first drop into an orbit making a close pass to the Sun, to maximize the solar energy input on the sail. Then the ship would begin to accelerate away from the system using the light from the Sun to keep accelerating. Acceleration will drop approximately as the inverse square of the distance from the Sun, and beyond some distance, the ship would no longer receive enough light to accelerate it significantly, but would maintain its course due to inertia. When nearing the target star, the ship could turn its sails toward it and begin to use the outward acceleration to decelerate. Additional forward and reverse thrust could be achieved with more conventional means of propulsion such as rockets. Similar solar sailing launch and capture were suggested for directed panspermia to expand life in other solar system. Velocities of 0.0005 c could be obtained by solar sails carrying 10 kg payloads. Using thin solar sail vehicles with effective aerial densities of 0.1 grams per square meter with thin sails of 0.1 micrometers thickness and sizes on the order of 1 square kilometer. Alternatively, swarms of 1 mm capsules can be launched on solar sails with radii of 42 centimeters. Each carrying 10,000 capsules of 100 million extremophile microorganisms to seed life in diverse target environments. The orbiting artificial satellites. Small solar sails have been proposed to accelerate the deorbiting of small artificial satellites from Earth orbits. Satellites in low Earth orbit can use a combination of solar pressure on the sail and increased atmospheric drag to accelerate satellite re-entry. A deorbit sail developed at Cranfield University as a part of the UK satellite TECHDMOSAT-1, launched in 2014, and is expected to be deployed at the end of the satellite's 5-year useful life. The sail's purpose is to bring the satellite out of orbit over a period of about 25 years.